Today in class 12th, I am taking a very important topic, that is the magnetic moment of due to an electron in the atom. We know that electron moves in the circular orbits around the nucleus in the atom, and this electron produces the current. So the moving electron is just like the current loop, and we know that whenever there is a current, there is the magnetic field. It means that this will behave just like a magnet. This is a small magnet that is called the atomic magnet. So today we will discuss about the magnetic moment due to the electron in the atom. We are having this is the nucleus plus Ze, and this is the electron. And it is moving like this in the clockwise direction. So it has the velocity. This is now velocity. Similarly, here this will have the velocity in this direction. This is now velocity. Now this is clockwise motion of the electron. Clockwise. Clockwise motion. Then this electron will produce the current. Since the electron has the negative charge, so current will be in opposite direction of its motion. So the current will be anti-clockwise. In clockwise orbital motion of electron, the current will be anti-clockwise. Anti-clockwise. It means that current will be like this. This is the current I. So if I take my right hand like this one, my fingers are in the direction of the current, then this thumb will be away from this plane of the board or this plane of this orbit. So we can say that this will produce the magnetic moment which is away from this one. So this is like this. This is the nucleus and this is the current. Current is in the anti-clockwise direction. This is now current. This is now current I. Then magnetic moment will be just perpendicular to this one. So this is like this. This is the magnetic moment M. So what we have, that when we are adding to this one, then this face appears just as the north pole, and this is now south pole. So this will behave as a magnet, anti-clockwise. the moving electron behaves like a closed current loop. So it produces the magnetic moment. It gives magnetic moment M. If suppose the electron is moving anti-clockwise, then the magnetic moment will be just downward. Suppose this is the orbit, this is the nucleus, and the electron is moving in this way. This is the electron. Then the current will be in this direction. So current will be like this one. This will be the current. This is the current. It means that the magnetic moment will be just opposite to this one. That I have to list in this way. Just I take it, this is the magnetic moment. This is just inside this area of this orbit. So now magnetic moment moment M equal to I into A. I the current, A the area of the A equal to pi r square, where r is the radius of this. This is no radius r, and I equal to E upon T. T the time period. So M equal to E upon T into pi r square. E upon T equal to 2 pi r upon B. This is now your pi r square. So this M equal to EV r upon 2. This is not so much. This is the classical view of the magnetic moment. It is classical view of magnetic moment. Now here R radius of orbit and that V equal to velocity of electron. But quantum mechanically this is not so. So quantum mechanically the magnetic moment upon angular momentum this is equal to G into E upon 2m. This is with a minus sign. Since electron has the negative charge, so we have taken the minus sign. Or we have this magnetic moment M upon L equal to G into minus E upon 2M, or M equal to G into minus E upon 2M into L, where L equal to angular momentum, and we know that this L is equal to mvr, and this is equal to n into h upon 2 pi. Now this n equal to 1, 2, 3, 4, 5, 6. This is the principal quantum number. Principal. Quantum number. And this represents the order of the orbits, the first orbit, second orbit, third orbit, like this, and this h is equal to Planck's constant. Planck's constant. So now if we put to this one, then this G, this is called Landé splitting factor. Landé splitting factor. M, the mass of the electron, as I have written here, M, the mass of electron. Electron. So what we write? That is M equal to G into minus E upon 2N into L. This is now your N into H upon 2 pi. So we will have this G into minus EH upon 4 pi M into N. This is now the factor now here this for orbital motion, and the electron have the two kinds of motion, one the orbital and second the spin. So we are considering the orbital motion of the electron. So for orbital motion, G equal to 1, and for spin motion, G is equal to 2. So we are taking the orbital orbital magnetic moment. So this M equal to minus this is equal to N into minus EH upon 4 pi M. So much. So EH upon 4 pi M. This is called the Bohr magneto. The term minus EH upon 4 pi M is called Bohr magneto. Bohr magneto. denoted by this is a magnetic moment mu. This we write it to become mu in place of n. This we have written. This is now mu. So this is mu, and this is also now this mu. This is also now mu. Generally we use the term for magnetic moment, that is now mu, denoted by mu b. And now this mu b equal to minus EH upon 4 pi m. Now if you put all the values, then this comes out to be minus 9.27 into 10 raised to the power minus 24 joule per Tesla. T means Tesla, here T Tesla. Tesla. So this is the value of Bohr magneton. It means what? That this gives you, now this mu is equal to. So mu equal to n into mu b. N into mu b. This is not so much. So we can say that the magnetic moment is the integral multiple of Bohr magneton. So this is the minimum value of the magnetic moment. Thus magnetic moment is integral multiple of Bohr magneton. So this is what the quantum mechanical view. Thus magnetic moment is quantized So minimum magnetic moment is how much? Minimum magnetic moment is equal to mu b, and this is equal to minus 9.27 into 10 raised to the power minus 4 joule per Tesla. So all the way, suppose we are having n equal to 2, 3, 4, 5, 6, then this will be the integral multiple of this one. So this scenario, in the first orbit, this is now so much, second orbit, this will be multiple of this one, and third orbit, this is multiple of this one. So in every orbit, if we know the value of n, then we can find what is the magnetic moment due to the electron. So now from here, n equal to 1, 2, 3, etc. So now if we have mu1 ratio, mu2 ratio, mu3 and so on. This is equal to 1 ratio, 2 ratio, 3 ratio, 4 and so on. This is not like this. So this is the magnetic moment is always the multiple of the natural number 1, 2, 3, 4, 5, 6, 7 and so on. So now this gives you the idea that the minimum magnetic moment is possessed in the first orbit of the electron. The minimum magnetic moment is in first orbit or Bohr orbit. Bohr orbit in atom. This we have considered the orbital motion. If we take the spin motion, for spin motion of electron, now this mu s the magnetic moment this is equal to 2 into minus E upon, or this is mu s equal to G into minus E upon 2m into the S. S is the spin angular momentum. S equal to spin angular momentum, and this S equal to this is now your spin quantum number, that is denoted by this h upon 2 pi into s, the small number s. So this s is the spin quantum number. This is now spin quantum number. Spin quantum number. Spin quantum number. So we can have again this mu s is equal to minus, now for this G is equal to 2, G equal to 2 for spin motion. So this mu s equal to mu s equal to 2 into, now if we put these values, then this is now minus EH upon 4 pi m into S. So now this again we are having this magnetic moment, this Bohr magneton, and this S will be depending upon this value is equal to 1 by 2. Or this mu S equal to 2 mu V into S. So this magnetic moment is more in comparison to orbital spin motion or orbital motion. This magnetic moment is more than the magnetic moment due to spin motion. Spin motion of electron is more than angular magnetic moment due to orbital motion. Of electron. It means that spin motion is more effective in comparison to the orbital motion. So if we find the resultant of the two, that is the magnetic moment due to the orbital motion and that the magnetic moment due to the spin motion. So that will be the vector sum of this mu L and mu S. The resultant magnetic moment is equal to the magnetic moment due to orbital motion plus magnetic moment due to spin motion. So this term is generally given by this mu equal to mu L plus mu S. Mu S, mu L, the magnetic moment due to the orbital motion is denoted by mu L, and due to the spin motion is denoted by mu S. So mu L plus mu S. This is the vector sum of the magnetic moments, because magnetic moment is a vector quantity. So we have that whenever the electron in the atom that is having the orbital motion and the spin motion, then most of the magnetic moment is due to the spin motion. But generally when we take the classical quantum mechanical view, then we are not, this spin motion is not given in the book, that the magnetic moment to be due to the spin motion. So here we have only the knowledge that the resultant magnetic moment must be equal to the vector sum of the magnetic moment due to the orbital motion and the spin motion of the electron. So we see that in the atom, the electron behaves like a small magnet. The conclusion is the moving electron in orbit behaves like a small magnet called atomic magnet. This is the conclusion. So moving electron is, this is either having the orbital motion or having the spin motion. Because of both, this will have the magnetic moment, and definitely the magnetic moment due to one electron is always affected. But in the orbits there are having the number of electrons there. So all the electrons contribute to the magnetic moment. So that I will discuss in the case of dimagnetism, paramagnetism and ferromagnetism, that what is happening when this they are subjected to the magnetic field, whether they get the magnetization or they get not the magnetization. So this is about the magnetic moment of the electron moving in the orbit of an atom. So thank you very much.